Hello everyone and welcome to the 40th lecture of the course Advanced Structural Analysis. This is the last lecture on the week 8. We have discussed to some extent the basic method of the matrix analysis. We are considering the stiffness approach as our primary form because it is more compatible for the computing system. And starting with the beam plane trusses, we looked into the problem of the plane frame as well as the grid into this week. Now as we consider the plane structures to somewhere comfortable to us and we have discussed the basic detail related to it, we move to the space structures, and as a basic understanding what we typically have seen in the previous sessions as well, that the stiffness approach is a very systematic approach which has been designed with a set of steps which can be followed through the various parts of the skeletal structures in the similar manner. Only what typically changes is the amount of the stiffness matrix or the element stiffness contribution, which may differ from the different form of the skeletal systems, and then the specific transformation which this the part of the skeletal structure will be taking up. When we go with the simple beam structures, we identified that the system is identified in the one plane only, which is the simple one dimensional object, and the global degrees of freedom as well as the local degrees of freedom, they both coincide. So there is no need for the transformation. When we moved ahead with the plane trusses, we realized that the local coordinates and the structural or the global coordinate of the system, they differ in the given plane. So we came up with a very simplistic in plane transformation which was defined with respect to the two translational components. For the frame structure, we included one more component of the rotation in that, but the transformation relationship was more or less same. When we went to the grid system, we realized that now the aspect of the grid system is considering a transverse displacement which is out of the plane of the grid members, and then there are two moments which are appearing in the same plane in which the grid structure is defined, and that way we were able to identify the transformation matrix for the given system also. Now looking at the specific structures which are typically 3D like the space frames or the space trusses, we need to realize that now the transformation has to be adopted with a 3-dimensional system, and that is the intention of the present topic which we will be trying to cover through the next few lectures. As we have also said in the last session that some of these contents are a little bit advanced. Of course, the course is itself an advanced level course. So these content will require a sufficient level of understanding even beyond the classroom. So you have to and also when it comes to the 3D spaces, sometimes the realization and the visualization of these spaces takes time because everything has to be seen from the general 3D perspective, which we cannot directly show in a 2D sheet or a 2D screen in a simplistic manner. So it is expected that when you go through the content, you also try to see it again. Maybe you can also refer it through the standard text which is referred in the course, and that will be making things more clearer for the general implementation. So as we move through the content, we have a transformation of the 3D spaces, the member stiffness which will be identified for the given system, and then we will also look at the general procedure of the solution approaches. As a first part, we will look at the transformation in the 3D space. So if we look at now a 3D object, up to now whatever calculations or the structures we were dealing with, they were all defined in one given plane. So the members of the given structure were always in a given plane, whether it was a plane frame or a grid system or a space or a plane truss or say the beam structure. Now the moment we have a 3D structure, we typically can identify it in a manner that say this is the origin point. So if this is the origin point of the system, I can consider it to be having say some initial coordinates of 0. Now along the direction of the x axis, I have located the coordinate which is the structural axis of the x. Along the y direction we have the structural axis, and along the z direction we have the structural axis. Now there is some identified set of line element. We are considering this to be the part of the same skeletal system. It could be the part of the truss member, it could be part of the frame member, but as we consider skeletal systems, so generally we adopt that the given systems are identified like line elements. So this element is located with respect to the position of 0 0, and then somewhere it connects it to a point which is differently not on the same plane, it is somewhere having its component. Now if I can define it with respect to the coordinates, that it is having a coordinate of x y as well as z in the given system. So, if you locate the distances between the system, say this distance is a, this vertical distance in the y axis, say it happens to be, and this distance happens to be c in the given system. So, I can realize that yes, this point is having a coordinate of a, b and c in the given system. So, it is not a system or a element which is existing in a simple 2D plane, but rather it is a system which has come out of the given plane now. So, as long as you were dealing with the plane system, we were only concerned about the two axes or the two coordinates of the given system. Now, we have to also look around the third coordinate of the given system. As a transformation in the given system, what we realize, now I may come up with a completely new. So, this is the structural system the way we have defined. Now, for the same member, I am not changing the member, but for the same member I am now coming up with a different coordinate system which is aligned in such a manner that this is the structural axis, say for the member, this is the this is the x axis for the member, this is say the y axis for the member coordinate, and this is say the z axis for the member coordinate. Even I did not take necessarily the member axis x along the length of the member. We can just come up with the more generalized case first, and we realize that for the same vector I can again come up with a differently existing coordinate system, and now I need to come up with that what is the relationship between these member coordinate systems which have been identified, or the local coordinate system, and the structural coordinate system or the global coordinate systems which have been located in the given problem. So, in necessity what we are looking for a transformation relationship between you can rate it with respect to the x, or you can write it in terms of the same notation of the a. So, I can call it as a of xm, a of ym and a of zm, which are the three components in the member ordinates or the member directions, and what are their relationship with respect to the component with respect to the structural system, which are a of xs, ys and a of zs in the given system. So, of course, there is necessarily a 3 cross 3 matrix which will be connecting these three number of components for the member and the structural system, but our understanding is now that what is this rotation matrix which typically will connect the two systems. So, when we look them together, we actually are dealing with a problem like this, where there is a same vector term. It could be represented in the regular structural system, say the x, y and z directions along the structural system, which is represented by the superscript s, or we can also be looking for a system which is located now along a different coordinate system, but for the same problem or the same element, and that is associated with some member coordinates of the given system. In most of the situations up to now, whenever we were making the transformations, we were considering that one of the axes remains same. Like if you recall the transformation when we were making only in the 2D plane, we considered that yes, this is the axis x, this is the axis y and this is axis z. We made a transformation for the x prime and y prime as the two axes, but we did not move the z axis. We considered that the z prime or the new z axis is still about the same axis. So, it is like saying that you consider a sheet, but you just rotate the sheet about the normal to the given plane, so that the normal does not change. But now as a general transformation, we are trying to bring a condition where the object which was initially defined now has been completely rotated with respect to all the possibilities of the axis of x, y and z of the given system. So, as we understand that typically when we look at this kind of understanding for the simple 2D system, what we did, we considered that x prime will be making some angle with the original x, some angle with the original y. Similarly, y prime will also be making some angle with the original x, some angle with the original y, and those are typically located as the direction cosines of the given system. So, the standard way of identifying the transformation rule is to identify the direction cosines, because that helps us to identify the components of the given system. So, if I look at the x prime, ideally what we generally do, we say that x prime means that there is some vector which is a vector I cap plus b vector j cap, where along the direction of the I and j we are along the direction of x and y, we are considering the I cap and j cap as the unit normals of the given system. So, knowing this idea or the unit normal along the direction of the x prime, I can consider that I can convert this into a unit normal. I can say that this is a divided by the square root of a square plus b square, which is the magnitude of the given vector. Similarly, b upon square root of a square plus b square, and that is the given vector. So now what typically this is the component, this is the component of the given vector which has been identified along the x prime direction on the x axis, and that typically we describe as the direction cosine with respect to the given vector term. Similarly, what we define as the second component is the or the second term of the j prime component, that is the component of this given vector on the y axis of the given system, and this is what we describe as the second direction cosine of the given system. So, as they are defined with respect to the unit normal or the unit length of the given system, so we typically can represent them that this is cosine of alpha, which means that in terms of the given direction of the system and the original x axis, the angle between the two systems, that is alpha, and this term, the second term which we have, that I can define in terms of the cosine angle again, but between the x prime and the y axis of the given system. So, I can call it as say beta. So, it will be cos of beta in the given system. Of course, that cos beta, if we try to solve, it comes out as cos of 90 minus alpha in the system, and that eventually we write as a sin alpha for the given problem. But the understanding is that as a general vector which is being described for a given system in a space, I can always locate its components in the original reference coordinates by locating the direction cosines of the given system, and the direction cosines are the cosine angle between the new coordinate and the old existing coordinates of the given system, or rather I should say that the angle between the member axis and the original structural axis typically defines the direction cosines for the given system. So, with this idea in mind, now I come up with the understanding like this, that these are my three member axis parts, say a of xm, y of a of ym and a of zm in the given system, and the structural system are defined with respect to a of xs, ys and zs in the given system. So, the understanding is they could be the displacement, they could be the forces, but the simple thing is that they are represented with respect to the member and the structural coordinates of the given system, and they are now connected with a 3 cross 3 matrix which we have represented like this. So, as a general rule which we just defined now, we understand that lambda 1 1 should be the cosine angle between the direction which is the corresponding to the member direction 1. So, if I call it as the xm in the given system with respect to the x of s in the given system. So, the angle between the x of m, which is this given part, and the x of s, which is the original structural system, that cosine angle is the lambda 1 1 in the given problem. Similarly, when I look for the lambda 1 2, I realize that again it is written with respect to the same row, that means it is giving the relationship between the a of xm with respect to a of ys in the given system. So, this has to be the cosine angle between the x of m, the xs with respect to the new direction 1 of the system, which is a of xm, with respect to the original structural system in the direction 2, and that happens to be the y of s in the given problem. Similarly, I go to the lambda of 1 3 and I realize that this has to be the cosine angle between the x of m and the z of s in the given system, right. So, this is the typical understanding, the way we describe the direction cosines of the given system. I can now come up with the same idea and look at the problem for the lambda 2 1, and I realize lambda 2 1 is cosine angle between, now the 2 1 means I am looking for the relationship between a of ym, which is the new member coordinate with respect to the direction 2, and I am trying to relate it with respect to the original structural direction 1, 2 and 3 one after another, and these are the 3 multipliers which I have got. So, the lambda 2 1 can be written as the cosine angle between y of m, because which is the second member coordinate, with respect to the first structural coordinate of the system, that is x of s. Similarly, lambda of 2 2 I can define as cosine angle between y of m and y of s in the given system. Lambda of 2 3 can be defined as cosine angle between y of m and z of s in the given system. So, typically we can always understand that the first subscript is referring to the new coordinate and the second one is referring to the old coordinate of the given system, and that gives a very nice basis to identify the direction cosines of the system, and in general the transformation matrices. Now, at the same time I can move to the A of Zm, the third coefficients, and that could be defined as lambda of 3 1. I write it as cosine angle between the Z of m and x of s. Lambda of 3 2, I can write it as cosine angle between Z of m and y of s, and finally lambda of 3 3, I can write it as cosine angle between Z of m and Z of s in the given system. Right. So, this is the understanding, the way we look at the direction cosines of the given system. So, this emanate from a very simple understanding that when you are looking for this given vector which is located with respect to say a new coordinate, I can bring down its components along the directions of the original reference directions of the structural system, say A of s, y of s and z of s in the given system. The moment I get those components with respect to the unit value of the given vector will actually give me the direction cosines with respect to, or the angle, the cosine angle with respect to the structural coordinate A of Sm, xm of the given system. Similarly, I can now do the similar process for the ym and zm in the given system. So, this procedure is quite sufficient to transform the general 3D spaces. Of course, now we will look at the specific cases that what typical issues we face, but as a simplistic case from understanding of this problem, what we will try to do now, we will just take one case, that what if I am considering that this is my, these are my two axes, this is the third axis, say this is x, this is y and this is z axis, and now I am trying to consider the rotation such that only about the x and y I am bringing the new axes which are x prime and y prime, whereas the z prime is in the same direction, right. So, this is the new coordinate which is x prime, y prime and z prime, whereas the original coordinate is x, y and z in the given system. So, when you are now looking for the relationship x prime, y prime and z prime with respect to the original x, y and z, so ideally I can now utilize the same relationship the way I just defined now. I can call it that it is associated with lambda 1 1, lambda 1 2, lambda 1 3, lambda of 2 1, 2 2, 2 3, lambda of 3 1, 3 2 and lambda 3 3. Now, for any of the values I got that lambda of ij in general is the cosine angle between the so I can call it as that with x prime I, which is, say if I happens to be 1 it is the x, if I happens to be 2 it is y, if I happens to be 3 it is z in the given system. And then with respect to the old one, so that I can simply call as x of j, right. So, better would be that if rather than x, y and z I can just call it as x1, x2 and x3 axis, and for the second one I can call it as that x1 prime, x2 prime and x3 prime in the given system. So, this understanding probably now will be easier to handle in the system, at least in the notation form. So, now if I look at the understanding of the cosine angle, the way we look at it, lambda of 1 1, I realize that lambda 1 1 should be the cosine angle between the new x direction which is x1 prime and the old x1 which is the one over here. Ideally, we should measure the angle in the anti-clockwise sense. So, this is the angle which we are looking for. So, I may call that this is the angle alpha for the given system. So, this is the cos of alpha for the given, or ideally we can remember, we can say that this original angle is say alpha. So, this angle, the one which we are referring with respect to cosine of x1 prime and x1, original x1 of the given system, I can call that this angle is cos of 360 minus alpha, right. So, we have total angle of 360, out of that this alpha is remaining. So, this is what the anti-clockwise angle is trying to cover, and if we just know that 360 minus alpha, it is cos alpha itself. So, that is where we end up with the cos alpha, and in fact that is what we remember, that cos alpha is the transformation expression which we get in the given system. Similarly, if I go to lambda of 2 1, I get lambda of 1 2 for say, I define it as the cos of x1 prime with respect to x2 of the given system. Now, this is x1 prime and this is x2, and I am looking for the angle in the anti-clockwise direction from x1 prime to x2. So, this is the angle I am concerned about. So, I define this angle as cos of 90 minus alpha in the system, and this happens to be sin alpha for the given problem. Similarly, I go with lambda of 1 3 in the problem. This happens to be the cosine angle between x1 prime and x3 of the given system. So, if you recall that x3 is still normal to the given x1 x2 plane or x1 prime x2 prime plane. So, that means the x1 prime, which is this direction, will be having a 90-degree angle with the system. I cannot show it on the given plane, but you must understand that if x1 and x2 are in the given plane, x3 will be coming out of it. So, in that condition, if the rotation is just taking place about the x3, x1 prime and x3 will always make the angle of 90 degrees. So, with that part I can understand that this is cos of 90, which is 0 for the given system, and this brings us to the same expression which we know from the previous calculation, that this is cos alpha, this is sin alpha, and this is 0. I can further go to evaluate the expressions for lambda 2 1, lambda 2 2 and lambda 2 3, and I realize that those expressions. So, if I go with the lambda of 2 1, I realize that this is cosine angle between the x of 2 prime and x of 1. Now, x of 2 prime, if I look at, this is the x of 2 prime, and I am looking its angle with the x of 1, which is over here. So, let me just keep everything else. So, the angle which I am looking for is this part of the angle in the given system. Now, if this angle I am looking to evaluate, I can simply say that if this is alpha, this angle will also be alpha in the given system, right, because as both will be moving by the same margin. So, this measure of the cosine between the x2 prime and x1 can be defined as cos of 270 minus alpha. So, this is the total angle of 270, right, up to except this one part, this total is 270. Out of that, alpha is negative. So, I can write it as cos of 270 minus alpha. We realize that this is sine, and 270 minus alpha, that will be in the third quadrant, and that is why it will be coming out with the negative sign, and that is minus of sin alpha. So, I define this value as minus of sin alpha in the given system. Similarly, I go with the lambda of 2 2, and I realize that this is the cosine angle between x2 prime and x2 of the given system. So, the angle which I am looking to evaluate is actually the angle from here to here, right. Again, every time I am measuring the angles in the anti-clockwise sense only. So, if I look at the system, it is cos of 360 minus alpha, and we understand that this is cos alpha, and that is what the expression gives us, right. We can again do the same thing for the third row. We understand that the axis 3 is having a 90-degree angle with x1 and x2, only with the x3 it is having the same angle, and that is where we end up with 0 0 and 1 in the given system. So, this is a typical understanding by which we can realize that the direction cosines, the way we define, could be the standard order to replicate the transformation in the 3D coordinates. Now, with this idea in mind, we realize that for a given problem where the structural member axis is along the direction of the member, which means that in the previous part of the problem, the A of xm, if I consider this to be along the length of the given member itself, then at least one thing we are able to fix, and that is the member axis is located in a fixed orientation with respect to the axis of x, y and z. So, if the x, y and z happens to be the global axis of the system, so the user can easily identify the individual angles, the cosine angles of the given member coordinate with the original directions of the x, y and z of the given system. What does it mean? I can come up with, say, the coordinates of this point, say any of the point over here, say this is the joint j, say this is the joint k of the given system, and now with respect to the joint j and k, I can define the cos of alpha, which is the cosine angle for the given system, as x of k minus x of j divided by L, length of the given member. So, the cosine angle, which is the angle between the axis x and the new member axis of the given system, is easy to evaluate for the given system. In the same manner, if I go with the second, the member axis xm, the angle with respect to the y axis, which we define as lambda of 2 1 in the given problem, we realize that this lambda of 2 1 will also be easy to evaluate, and that will be y of k minus y of j divided by L, and finally lambda of I should call it as lambda of 1 2, and finally lambda of 1 3 we can again evaluate the component of this member axis coordinate along the axis z, original axis z of the system, and that could be defined as z of k minus z of j upon L of the given system. So, this is easier way to identify at least the direction cosines with respect to, so this we can also call lambda 1 1. So, the direction cosines which are identified, the 3 values, out of that at least the first row is easier to define provided that the member axis is considered along, or the member axis 1 is considered along the length of the member itself. So, with this idea now we are able to identify the first axis, but the question arises that how do we define the direction cosines for the other 2 directions. So, if I look at the expression here for lambda 2 1, lambda 2 2, lambda 2 3 or the lambda 3 1, 3 2 and 3 3, I require the direction of the member axis y and member axis z in the given system. But when we look at the cross section, the member axis y and z are not a fixed axis of the given system. What does it mean? If I have this as a cross section, along the length I have considered the axis x, but now on this cross section, if I just draw this cross section somewhere over here, I can have the member axis like this, which is the y of m and z of m. But at the same time someone can also bring a member axis and call that this is y of m and this is z of m in the given system. And there could be infinite such possibilities where the axis y and z for the member coordinate can be located on the given cross section plane. So, you can just think about it that if this is a pin which is being considered as a skeletal structural form, I can identify the local axis of the member along the length of the system, that is the x of m. But now when it comes to the y of m and z of m, I do not have a specific choice. I can keep the axis like one in this direction, another in this direction. I can also come up with a different 2 perpendicular or the 2 orthogonal directions. So, as the choice of the axis for the y and z directions is not fixed, so evaluating the direction cosines is not very straightforward. So, unless we do not fix the orientation for the axis y and z, we cannot identify the position or the direction cosines of the given system, right. Now, what will be the possible basis to fix the directions of the direction cosine or the axis of the given system? One possibility, so this is something which we have already discussed, that lambda 1 1, lambda 1 2, lambda 1 3 can be defined by these 3 expressions of the given system. Now, in order to know the axis with respect to the y and z, which are, as we said, that the choice is not very specific and they could be defined along any of the possible directions. So, then the first choice comes up, that when the user can keep the fixed and the specific directions for the axis y and z, and those choices typically come when user has a very standard sizes where the cross sections can have the principal axis, well defined principal axis. So, now if you come up with say a I section like this, then if I consider that this is being modeled as a structural or a skeletal system, this will be my x of m, the member coordinate or the member direction. Now, in order to get the y and z axis of the given system, the user has a very clear choice that y axis has to be along one of the principal axis of the system and the z axis has to be along the second principal axis of the given system. So, if you are able to rotate your I section in a different orientations, you will at least fix that what are the directions of your axis x, y of m and z of m in the given system, and that will help us to know that what is the specific orientation of the given system, so that the direction cosines can be calculated. But in the generalized cases, when we are not fixing the axis of the given system, we come up with some philosophy by which we can specify the directions in which the y of m and z of m can be identified, and then we try to implement that if a generalized relationship for the direction cosines can be obtained based upon that understanding. So, with this point in mind, we go with the following considerations. We consider that the z of m, which is the structural axis, the member axis z, should lie in the plane, in the horizontal plane of x of s and z of s of the given system. So, now looking at this system, we are trying to have a 3D visualization. I have tried to draw the figures such that one can understand that this is a 3D visualization of the given system. So, we have a first given system which is the direction x, this is the direction y and this is the direction z with respect to the structural system. So, at any given point I can consider that this is the plane which is the xs and the zs plane of the given system. Now, as we consider the member has been defined somewhere like this. So, the member axis x is well defined. I can define the x of m as the axis which is along the length of the member, and corresponding to that the user is able to identify lambda of 1 1, lambda 1 2 and lambda 1 3 in the given system. What user is not able to identify that where the axis z and y should lie for the given member system. Now, they could be in anywhere. So, one can be, if you are not able to comprehend that what typically this problem is about. So, you can consider a system which is generally in a 3D space. This axis is known to me, which I can locate in the member direction. But now, if the cross section is not fixed for you, you can keep it with respect to any of the orientation. The member z axis could somewhere be in this plane also. The member z axis could be located along this plane, this plane also. The member z axis could also be located in somewhere other, some different planes of the system. And the moment we define the z axis in this manner, the normal to that we can just bring the axis y m in the given system, right. But so there comes the main choice, that how do we specify that where the axis z should be lying on the given system. So, with this point in mind, what we consider the first assumption. So, the first assumption which we consider here, we consider that the z of m should be in the horizontal plane of x of s and z of s of the given system. That means, if this is the vector, we consider that in the given plane, somewhere on this given plane, we make a rotation and we try to bring the given member from the or we try to bring the new direction of the system somewhere on this given plane only. So, this is the plane which we are defining as a horizontal plane of the given system, and we try to say that z of m will be somewhere located on this plane, and this could be defined with respect to say some value of the angle beta in the given system, right. So, this angle beta which we are describing is the angle which is made in the xz plane of the given system for the structural system. So, you can consider it that if this is the y axis which is the normal and this is the x and z which is in the given plane, I am just trying to make a rotation with respect to the given system, so that the in plane axis rotates in the given system. So, somewhere like this, if this is the x of s and this is the z of s in the given system, and this happens to be the y of s axis. So, about the axis y, we are trying to make a rotation in the system such that the given x axis moves to this position. So, this becomes our x of m for the given problem. Of course, this is not the final x of m, but as a first step I am trying to bring it, and then this becomes our z of m in the given system. So, that is the two understanding for the given system, and we bring it with respect to some rotation angle beta in the given problem. So, that is why we call them as x of beta and z of beta in the given problem. So, with these two angles defined in the given problem, we can now locate that y of beta will be again in the similar axis as it was defined earlier, and we can consider this case as a simple rotation about the axis y, about the structural axis y of the given system, such that the given xs and the zs plane are rotated with the angle beta in the given system. So, this could be considered with respect to a simplistic variation like this, in which, so now if we consider that we have rotated the given system or the rotated the given vector plane such that the given system has come up to this axis. So, this is x of beta, this is z of beta in the given problem, and this is the y of beta, which is the specific axis in which we are having the about which we are having the rotation of the system. So, corresponding to this system, we can identify the rotation tensor, and that rotation tensor will be x of beta, which is the first axis, y of beta which is the second, and z of beta which is the third. They all will be located with respect to a standard rotation about the axis y itself, and that gives me cos beta sin beta minus sin beta cos beta in the given system. Okay. So, one can easily understand that I am doing the rotation with respect to the axis y, though here it is defined with respect to the coordinate direction which is in the clockwise sense, but now you can just identify the standard relationship in the same direction cosine form, and we realize that as the axis with respect to the x of beta and the x of s, we can calculate the cosine angle, sine angle. So, these are the specific values which are located with respect to the x of s and the z of s coordinate. Similarly, with respect to the z of s component, which is also now rotated by an angle of beta and has reached to the z beta component. So, we get the other two parameters of the transformation term, which is sine of beta and the cos beta in the given system. So, the understanding is that we just rotated first about the axis y by some angle beta, and we got the new axis which are aligned as x of beta, z of beta and y beta in the given system. Now, as a next case, what we consider that this is the x of beta axis which has been considered, but now this axis should be aligned same with the x of m, which is the member axis of the given system, because we want to locate our member axis in this direction. So, x of beta should actually rotate and get aligned with respect to the given member ordinate or the member length of the system. Now, this can happen only if the plane which we have identified over here. So, if you can now understand the plane which is made with respect to the x of m, which is the corresponding system of the line represented by this, and the y of s, which is this particular axis of the given system. So, this is a plane which is same as this given part also. So, if you look at this part of the plane which has been just taken out from the beta rotation system. So, on this plane now I want my axis zm to be ym to be placed. So, what does it mean? That I want to align the x of beta axis with respect to x of m. That can happen if I, so it is like saying that you put a sheet and you rotate it in such a manner that the x of beta goes in alignment with respect to, so from here it rotates by some value, say gamma, and it reaches and aligns with the direction of the x of m in the given system. So, if we try to show it, it is something like this, that x of m axis which was defined along the given member direction, I can call it as that x of m as well. So, this given x of beta is rotated by some angle gamma in the system. So, this everything is happening in this plane only. So, on this plane I am trying to make the rotation such that the given system is rotated about the z of beta axis. So, z of beta I am not moving now, about the z of beta I am trying to make the rotation, but the rotation is made such that the given axis ym, which I will locate now, should exist in the plane of x of m and y of s of the given system, and that is the same plane which I have located over here, x of beta and y of beta of the given system. So, the moment we do it, we get this as a axis which is x of gamma, because we are considering this angle to be gamma. This is the second axis of the system and we consider it to be now y of gamma in the given system, and finally, this is the originally defined axis of the system which is y of beta of the given problem. What we realize that as we are doing the rotation about the z axis, z beta axis of the given system, so we can write the expression as x of gamma, y of gamma and z gamma, which are the three new coordinates identified in the system, in terms of the three originally defined coordinates x of beta, y of beta and z of beta of the system. And this can be easily done by considering a simple transformation relationship in the x of beta and y of beta plane of the given system. And by doing this, we get the expression as cos alpha sin alpha minus sin alpha cos alpha, and with respect to the z we are not changing anything. So, this happens to be 1 in the given problem. So, we did 2 times rotation, one about the axis y, second about the axis new axis z in the given problem, and that way we are able to now locate at least the 2 points, one which is aligned across the member direction. So, this is our x of gamma or x of m in the given system. The second one which is identified over here is our y of m in the given system. So, I can consider it to be y of m in the given system, and this third one is the z of m of the given system, right. So, these are the 3 axes which we have got in the given problem. Now, this is done with the consideration that the cross section related changes are not there, which means that if I now at this point identify that on the cross section also I end up with the y of gamma and z of gamma not in the principal axis direction. So, I need to further make a rotation on the cross section plane of the system. So, this is the understanding that you initially started with the member somewhere. I will just try to make it like this, that initially we had this as the x of m direction, y of m and z of m directions we were not clear with. So, we identified some rotation in such a manner that the initial system which was considered, we first tried to rotate it with respect to the y axis. So, it got us on the given xz plane 2 new orientations of the given system. Once we got this, about this z axis we rotated the system of the x, the new x axis, say the x beta, and this y axis of the system. So, the moment we rotate it, this rotates into this new direction. So, we call it as x gamma and this we call as a y gamma in the system, and we keep this rotation about the axis z of the system, which is z beta of course. Finally, once we realize that y of gamma and the z of gamma, because z of beta and z gamma both will coincide with each other. So, if they both do not align in the direction of the principal axis of the system, so we also need to make one more rotation, and that rotation will be about the axis x. So, if it is about the axis x, so it is finally giving me a transformation rule like this, that x of m, y of m and z of m, the three components related with respect to the gamma components of the given system, which were the originally defined one, and these are represented as a multiplier of the represented. I think this need to be just modified. This will be x of gamma, y of gamma and z of gamma in the given system, and this will be x of m, y of m and z of m in the given problem. So, this relationship can be simply expressed in terms of the same in plane transformation rule. Only thing is, this transformation is taking place with respect to the axis x of the given problem. So, I think I just need to modify this. So, this one will be with respect to x of gamma, y of gamma and z of gamma, the new system which we are representing. Yes, or if I think I just need to define in the member coordinates only. So, if I just define in the same manner that x of m, y of m and z of m, the three member terms of the given system, they can be represented in terms of the gamma terms. Only thing is, the rotation is taking place about the axis z. So, I think the given components will give me about the axis the axis xm is the axis about which the rotation is taking place. So, I will be placing the given system similar to one which we have defined in the previous case. So, I will just modify it that this is cos alpha, this is sin alpha, this is minus of sin alpha and this is cos alpha in the given system. So, about the axis x of m, we just did this rotation of the given system from the y of gamma and the z of gamma plane to the new planes which are y of m and z of m in the given system. So, while doing it, the axis which is x of m or x of gamma, that remains same, that is not changing for the given problem. So, with this idea, now finally we realize that the overall transformation, as we typically do for the overall system, is so this is what we try to show, like so if we identify the overall transformation of the system, so we identify that these are the three directions, and we just did the transformation now on the cross section plane. So, rather than the y of gamma and the z of gamma being fixed, we just located two new directions of the system, but this transformation we did with respect to the same x of gamma axis. So, this remains x of m, whereas over here we get the y of m and z of m as the two new axes of the given system. Finally, with this part we realize that as we did these three transformation one after another, so if we want to get the x of m, y of m and z of m in terms of the original x axis or original x coordinates of the given system, so what we need to do, we need to start with the very first part, right. So, we have the first system where the x of beta was converted in terms of the x of s of the given system. So, if I just go back in the similar order, I just write that x of m is defined with respect to the r with respect to the last orientation. So, I call it as the r of alpha as a orientation in the system. So, r alpha into x of gamma, y of gamma and z of gamma, this is the last transformation. Now, we realize that x of gamma, y of gamma and z of gamma is already defined, that it can be converted with respect to the given rule that these three values can be written in terms of the beta components. So, I go with the expression that it is r of beta, sorry, r of gamma into x of beta, y of beta and z of beta in the given system. And finally, in order to convert this x of beta, y of beta and z of beta in terms of the original structural system, we define r alpha, R gamma R of beta in the given system, and that gives us x of s, y of s and z of s in the given system, right. So, this way we are able to identify, or we are able to convert the actual transformation. So, the final transformation which we are looking for is the multiplier of the three transformations R alpha, R gamma and R beta in the given system. So, if you are looking for a general transformation in a 3D system, one can consider it that we did one level of transformation with respect to the or we should start with the first one. We did first level of transformation with respect to the axis y and in the given xz plane. The next level of transformation we did with the new z axis, and we did it in the new x and the y plane of the given system. And finally, with the cross section of the geometry, we did the final transformation about the new x axis, and that gives us the total transformation of the given system. This could be simplified in this particular manner, which is identified for the general space structures. We will just try to briefly discuss that what individual values of the given system identify, and what are the expressions of the beta in the given problem also identify. With this, we stop over here. We have tried to briefly discuss the general 3D space transformations. These discussions are somewhere which can be related to both the space frames as well as the space trusses, and we will now try to look at the aspect of the general analysis of both of these structures. With this, we stop over here. Thank you everyone.